Okay, here we go. We are going to be looking at our last new idea, and it's not a particularly tough one. Our last new idea for the whole course, for Unit D, is even and odd functions. Now, when you're dealing with just basic ordinary polynomials, when a function's even or odd, all you have to do is look at the highest degree in the function, and it'll tell you whether it's even or odd. And I don't know why this isn't opening right away. I mean, you know what? Maybe I'll just try it again. Let's see, I'm going to close that and try it again. That's all we need is for one note to kind of be slow. Oh, okay. There we go. There we go. All right. So, obviously, if you have a... Oops. Hold on. If you have a function that is y equals x squared, well, that's very obviously an even function because the squared is on the x and squared's an even number. Even if you change that to x squared plus x, you still call it even because the highest degree makes it an even function. And why we care about whether it's an even or an odd function is because it tells us what the end behavior of the function's doing. The even functions will have both arms going in the same direction, and the odd functions will have one arm going in one direction and the other arm going in the other. Even more important than that, when you're actually trying to sketch a curve, is the symmetry that you get from even and odd functions. A function is even if it satisfies the property f of negative x equals f of x. So if you substitute in negative x for all the x's and you get the exact same function you started with, you have yourself an even function. Let's take a look at the two examples here. I have y, can you see that? Let me make that bigger. You have y equals x squared, or f of x equals x squared. And if you take f of x equals x squared and you plug in f of negative x, notice you still get x squared. F of negative x equals f of x. The same thing is true for this one. And even though I don't know this equation, it's going to be something a little more severe than these two equations, I know that it would work that way because graphically, even functions are symmetrical across the y-axis. So by my new definition of even, let me just go back for a second. Technically, this one actually wouldn't be even because if I called this f of x instead of y, and I plugged in f of negative x, notice I would get, this is still x squared because negative x squared is just x squared, but instead of plus x, it would be now negative x. So if you would have called this an even function in grade 11, because you were just talking about it as a basic polynomial, in calculus we don't call it even anymore. This is in fact neither. It's neither odd nor even, which means it lacks the symmetry that we're talking about here, where I can treat the y-axis like it's a mirror, and it's a mirror image on the left and right side of the y-axis. Now, odd functions, again, this is just a basic odd function, but would it be an odd function if it had, say, an x squared part on it too? And the answer is, according to calculus, no, because a function is called odd if when you plug in negative x and run it through the equation, you get the exact opposite function that you started with. So if you had, for example, f of x equals x cubed, yes, that's an odd function, because if you try putting in f of negative x, you get that the function exactly is the opposite of what you started with. If you had the function y equals, or again, let me change that to f of x. If you had the function f of x equals x cubed plus x squared, and you tried plugging in, oh, hang on a sec. My pen's not working properly. There we go. F of negative x. This part becomes its opposite, but notice when you square a negative, it's positive. Be careful. Is this thing exactly the opposite of that thing? No, because this would have to be a minus. So this is, again, neither. But if I had, say, function g of x was x cubed, say, minus x, and I said, okay, let's plug in negative x and see if it's odd. The first term becomes its opposite. The second term becomes its opposite. So yes, this one's definitely odd. And graphically, odd functions have symmetry too, but it's a little harder to kind of explain and demonstrate. An odd function is symmetrical with respect to the origin. It's symmetrical around a single point. Put another way, if you can picture rotating the graph 180 degrees about the origin, and the graph looks identical to the way it looked before the rotation, it has odd symmetry and it's an odd function. So take a look at this guy. Here's again the function's x cubed. If you just take this arm and you rotate it 180 degrees that way, it becomes this arm. If you take this arm here and rotate it 180 degrees that way, it becomes the other arm. Here's a little more fancy one. This looks like it's some sort of cortic or something. And if you take this arm on the right and you rotate it as if you're rotating it around the point 0, 0 by 180 degrees, you will get the left arm. So there's some examples of odd symmetry. And if I know a function is even or odd, that really cuts down on the amount of effort I have to put into making a sketch, because I know that once I have half of it, I can just reflect the other half. So that's the last kind of new idea in curve sketching. And from here, what we actually do now is we put all of the ideas we've done in all of Unit D together. And there we go. And this is our last handout right here. It's called Putting It All Together. I think it's just called Curve Sketching if you're looking for it in your own OneNote. And let's also remember that I gave you kind of a nice list called the cheat sheet, where you can kind of look through all of the things here that you can figure out about your function. I didn't put even and odd symmetry on here because we gave this to you before the last assessment, and you hadn't talked about that yet. So you could even add that in here if you like to your little cheat sheet. But let's start going through this example. Okay, we've seen this one before. We've actually played with this example a couple of times. So I'm going to just save some time. I won't bother showing you the derivatives. You should be able to find derivatives for yourself. So let's start going through it kind of one thing at a time and looking at what we can find out about this function before we try to sketch it. Okay, so first of all, where is it increasing or decreasing? So you find that out by taking the first derivative and setting it to 0. So 0 is equal to negative 4x all over x squared minus 1 all squared. And of course, what am I looking for? I'm looking for the critical values, right? So multiply both sides of the equation by x squared minus 1, and I get 0 equals negative 4x. So x equals 0 is one critical value, okay? But you also have critical values where this thing does not exist, right? So your critical values are the ones where you have the derivative of 0, and then the derivative wouldn't exist if x was plus or minus 1. So there's my critical values. So I'm going to make myself one of my usual interval charts. So furthest left is negative 1. And then I have to consider the interval between negative 1 and 0. Then I have to consider the interval between 0 and 1. And then I have to consider the interval more than 1. And I have two factors here, right? I have the factor negative 4x. Okay, and then I have the factor x squared minus 1 squared. And then, of course, that tells me what the derivative's doing, and that tells me what the function's doing. So, what do I know about this function? Well, let's see. Notice that I can save some time here. This column will always be positive, won't it? Right? Because I'm squaring whatever comes out of that bracket. So really, it's the first one I got to worry about. And if I put in a number less than negative 1, this thing is positive. So the function's positive. So we are increasing. Right? And then if I put in a number between -1 and 0, it's still negative. A negative times a negative is still positive. Positive, increasing. So we have no change in whether we're increasing or decreasing at -1. So -1 is not a maximum or minimum, which is kind of the thing I'm going to do below here. If we put in a positive, this is now negative, and we're decreasing. Aha, we had a change from increase to decrease. And when x is greater than 1, again, that becomes negative, negative, decreasing. So I didn't give myself a whole lot of room here, so maybe I could just, I have an idea. I'm going to just, maybe make that a little smaller. I know, that's cheating. You can't do that in your notes. I'm going to say then, therefore, f is increasing from where? Let's see. So we're increasing from -infinity to to 0, right? It's increasing all the way through that interval and through that interval. So it's increasing from -infinity to 0, and f is decreasing from 0 to infinity. So there we go. So there's our first step. Now, the answer to this one leads us to this one. A change between increasing and decreasing tells us that we have a local maximum, and I can say that therefore we have a local maximum when x is 0. I'll go back to my original function and figure out, okay, when x is 0, that means y is 0. So the point 0, 0 is a local maximum, and that's the only maximum we have because it's the only place where we change from increasing to decreasing. We don't have a local minimum anywhere, so there we go. All right, now let's deal with the other derivative. The other derivative is what we're going to use to find concavity, and that, of course, is where we explore what happens with the second derivative. So we set the second derivative to 0, giving us 12x squared plus 4 all over x squared minus 1 cubed is equal to 0. And again, I'm concerned about where this derivative is 0 and where it doesn't exist. So once again, it doesn't exist at x equals plus or minus 1. And in this case, though, there's no place where this one is 0, right? Because when I multiply both sides of the equation by x squared minus 1 cubed, I get x squared plus 4, or sorry, 12x squared plus 4 equals 0. And move the 4 to the other side, divide both sides by 4, whatever you want to do, you end up with x squared is equal to the negative, that would be, let's see, what would that be? Negative 1/3. And of course, there's no solution to that because you can't square root a negative. So there's no point at which the concavity changes because you've hit a critical value. You're not supposed to call those ones critical values according to most textbooks. But there's no place where because the second derivative is 0, you have a point of inflection. But the places where it doesn't exist might be. So I'm going to have to explore those. So once again, I'm going to make myself a little chart. Okay, but I don't have to worry about the 0 point. So forget 0. It's just what happens when I'm below -1, what happens when I'm between -1 and 1, and what happens when I'm bigger than 1. And my two factors this time are 12x squared plus 4 and x squared minus 1 cubed. And I know I'm kind of going a little further than I should, but I need to write big enough so you can see it. I pity anybody who's trying to watch me on a phone right now. Okay, and that tells us how the second derivative is behaving, which tells us how the function's behaving. Okay, if you plug in a negative here, it doesn't matter. You're going to get a positive. If you plug in a negative here, you're going to get, well, let's see. If you plug in a negative smaller than -1, you'd get, like, say, -1.1. That would become a positive bigger than 1. So that's a number bigger than 1 minus 1. That's positive. A positive cubed is still positive. So that's positive, which means we're concave up, right? Now, a number between -1 and 1, like, say, -0.9, this one's still going to be positive, but this one now is going to jump to being a negative. So that means that the function's behavior is negative, which means it's concave down. And then x is bigger than 1. Again, both of these guys are going to be positive, so that means that we're concave up again. So concavity changes, so I'll say therefore we are concave up from negative infinity to negative 1, and then again from 1 to infinity. We're concave down from negative 1 to 1, and because we changed concavity at negative 1 and 1, I would call those points of inflection, but maybe I should call them potential points of inflection. Of course, it's only a point of inflection if it exists. So I'm going to say, I'll explain this in words, f prime prime of x changes from positive to negative and vice versa at x equals plus or minus 1, but these points are non-permissible, right? Don't forget what the original function was, right? The original function was x squared minus 1. So x can't be plus or minus 1. So it's not like that's a point where you could have an inflection and a change in the curvature, because that point doesn't actually exist. So therefore, this function doesn't have any, I'll just say, no points of inflection. So we don't have any minimums. We don't have any points of inflection. Do we have any asymptotes? Let's explore that. So for the horizontal asymptotes, you are exploring what happens as you go to infinity and negative infinity of the original function. Don't make the mistake of accidentally starting to play with the limit of one of the derivatives. You go back to the original function. And remember, your trick here, your algebra technique, is to divide by or times by 1. But your 1 in this case is 1 over x squared divided by 1 over x squared. And here's where you now have to consider direction. All right, those x squareds cancel. So you're going to get 2 over 1 minus 1 over x squared, right? Now, if this number is heading to infinity, that's 1 minus something infinitely small. So that's going to be just a 2 over 1, which is 2. Do I need to recalculate that for the other limit? So the other limit is what happens when you head to the left forever. And please notice, I'm just going to look here. Up to here, the algebra doesn't change. But do I end up with a different number than 2 if this is going to be infinitely small? No, because minusing a negative is like adding a positive, and 1 added to something infinitely positively small is still basically 1, so that's still 2. So both of these limits from the left and right side are approaching the asymptote 2. All right, let's try vertical asymptotes. Now, vertical asymptotes are where you look at the original function's non-permissible values, and they're not permissible at plus or minus 1. So I have 4 things to consider here. First, I consider the limit as x approaches 1 from the left of 2x squared over x squared minus 1. And this is the one where there's no real algebra trick here. You just have to kind of reason it out. So if you're approaching negative, I should have said negative 1. Thank you. I said negative 1 and I didn't write it. Or did I say 1? I didn't mean to. Negative 1. There. If I'm approaching negative 1 from the left, that'd be like, say, negative 1.1 or something, or negative 1.001. When I square that, this thing is actually going to be positive. So it's going to be 2 over 0, but approaching 0 from the positive side. So that's actually heading to positive infinity. Right? If this is a negative, it'd be heading to negative infinity. But no matter how infinitely small this gets, it's still an infinitely small positive number. Now let's think of the limit as x approaches negative 1 from the right. Now from the right, when you approach negative 1, you'd have something like, say, negative 0.99. And that's going to make the denominator basically shrink to 0, but it'll always be negative. So it's heading to negative infinity on the other side of the asymptote. That's really important when I need a picture of what this thing's doing, is I need to know on which side of the asymptote is it going up and on which side is it going down. Similarly, if I'm approaching positive 1 from the left, I'm getting 2 over 0 negative, right? Why negative? Because again, from the left, at positive 1, it'd be like, say, 0.99. That makes the bottom negative. So it'll be getting infinitely closer to 0, but it'll always be negative. So there. And then the last one, what if I approach the 1 but from the right? And you can see that that means that the bottom will always, this number will always be bigger than that number, just getting infinitely smaller positively. So it's going to be 2 over 0, but from the positive side of 0, which is positive infinity. All right. Some minor details. X-intercepts, though that's actually pretty easy. Go back to the original equation and set y to 0. You get basically the point 0, 0. And of course that is your y-intercept. And there is of course one last thing that we just talked about. We do have some odd or even symmetry we can test. And we can test that by trying what happens when we go f of negative x. So f of negative x would be, let's go back to the original function again, what was it? It was 2x squared over x squared minus 1. So that's 2x squared over x squared minus 1. That's going to be the original function. Therefore, we have even symmetry, which means when we graph it, just graph the left or the right side, and then you can just copy it because you know it's the same on either side. Okay, I'm ready to graph this now. I think we stuck all the graph paper at the end. Am I right about that? Come on, picture. There you are. All right, so let's graph this picture. So what do we know about this thing? Well, we know we have our one and only local maximum at 0, 0. We know that we have asymptotes vertically. Here and here at plus or minus 1. We know we have a horizontal asymptote at 2. We know that as we approach negative 1 from the right, we head to negative infinity. We know that as we approach positive 1 from the left, we head to negative infinity. We know that that's the only local maximum we have. Everything else is concave up in this picture. The only concave down was between those 2 points. And so we know that we're approaching 2 as we go to infinity left, and we're approaching positive infinity as we get closer to negative 1 from the left. And we know it's symmetrical, so this arm has to look exactly the same as that arm. And that's it. All right. As always, I'm just not happy unless I have some sort of check. And so I'm going to go to my Desmos, and my Desmos is going to tell me whether I got this right or not. And let's see. Let's compare to the Desmos. Where are... Oh, wait. Am I not logged in? Oh, yeah, I'm logged in. I think this... Oh, example 1. That's it. Open graph. There it is. And let's see. Moment of truth. Pretty good. And some of you might remember this in grade 11. I think we nicknamed this one the driveway graph in grade 11. So there's the calculus way to get a driveway graph. You might be going, hey, I could have made this graph in grade 11. Yeah, but of course they get more complicated than this. But all the tools we used are the ones you'd use even if the curve gets more nasty and more complicated. So there we go. So there's our first example. You know what? Tomorrow we'll do a different example. It'll actually be even easier. And then we'll let you work on 5.5 questions. If there's people who want to get started on the 5.5 questions now, by all means go ahead. Remember that you can kind of always follow these steps here on your curve sketching sheet. Notice I kind of followed this order when I graphed it. I actually put this point down first. I guess I did B first. And I knew B and C were the same thing. So I guess I did B and C first. But usually I sketch the asymptotes first. And then that's it. That's how we do them. Okay, I'm going to stop the lesson.